We will now proceed to the plenaries. For the first plenary of the day, we have Prof Jack Dongarra, who unfortunately is unable to join us today, and has sent us his pre-recorded talk on an overview of high-performance computing and the importance of AI ML and future requirements. We will now start the video. Please enjoy.
This is Jack Dongarra from the University of Tennessee. I'm the most recent recipient of the ACM Alan Turing Award, and I'd like to welcome you to the Global Young Scientist Summit. I'm going to talk about an overview of high-performance computing and the importance of machine learning and artificial intelligence and some of the future requirements. Simulation is really considered a third pillar of science today. We have two pillars of science. The first one is theory. That's where we do a paper and pencil kind of design of things. The second one is actually building an experimental facility or construction to carry out the theory that we just put down on paper. So theory and experiment go together. And today, we use computer simulation to augment those two. And the computer simulation is done because sometimes it's too difficult to build a physical experiment. Sometimes it's too expensive to conduct that experiment. Sometimes it's too slow to understand how things are going to evolve from the theory. Think of two galaxies colliding. That's an experiment that we really can't put together, but we can do a simulation of two galaxies colliding on a computer. And the same thing is true for climate. If we want to understand how the climate's going to evolve in the future, we could wait and see, but more importantly, we can conduct a simulation of that climate through a model that's been developed, and that will give us insight as to what's happening given the conditions that we have today. So computational science is a paradigm that augments theory and experimentation. It's considered this third pillar under which we do scientific discovery, and we use high-performance computing systems to do many of these simulation experiments. And those simulations are done on those supercomputers. So a supercomputer is today, a typical supercomputer is based on commodity processors. So we have a chip, maybe from Intel or AMD, and that chip has many processors on it. Those processors are called cores, and those cores sit on that one chip. They can carry out a computation using parallel processing, the ability to use those cores to help in solving one problem. And there's some memory associated with those cores as well. But we're not going to stop there. We're going to think about taking a board, and we're going to put multiple chips on the board. So we have chips now which have multiple cores, and we're going to put multiple chips on a board. So we have a large number of cores now on a board, again, with some memory. They're shared memory in the sense that each of those cores can get access to the memory quite easily. But those cores are limited in some sense in terms of their computational power. So we often think of augmenting those chips with graphical processing units, or GPUs, and those GPUs are there to boost the arithmetic intensity to help with getting more floating point operations in our computations. So we can offload things from that chip to the GPU. The GPU would carry out some computation and then send the results back to the chip. That's the way they're usually interconnected. And of course, we're not going to be satisfied with one board. We're going to think about having multiple boards in a cabinet connected through a network, so we can pass information from one process to another process in the course of doing a computation. That one cabinet is of course not going to be enough for carrying out the computations we're thinking about. So we think about filling up a room with a very large number of those cabinets. And you should think about the area of this, roughly the size of 2 tennis courts would be the right approximate size. And we have a number of supercomputers which have been designed and built and are in operation today. There are some Chinese supercomputers. There's a supercomputer in the US, which is considered the fastest supercomputer, built exactly on these principles of taking commodity processors, putting them on a board, augmenting that with an accelerator in the form of a graphical processing unit, and putting many of them together in cabinets and connecting them together to form a single unit, which we do parallel processing on to effectively compute the solution. So today's environment for scientific computing is really highly parallel. It uses distributed memory. That is, each of the nodes of this computer has its own memory. And in order for a node to share information with another node, it has to engage in a message passing paradigm. And for message passing, we use a programming model called MPI, the message passing interface. And we also use something called OpenMP as the programming paradigm when we share information on one of the nodes itself. The fastest computer is this computer at Oak Ridge National Laboratory. It's a Department of Energy laboratory, and it has roughly 8 million cores in it. So 8 million cores, 9,408 nodes in this computer. They use parts from the company AMD. AMD CPUs and AMD GPUs are in this computer, the supercomputer. And if we take a look at where the performance is, 98% of the performance comes from the GPUs. So you really need to be using those GPUs in your computation, that offload of the computationally intense parts, and doing that on the GPU. So we have this heterogeneous collection of commodity processors and also commodity GPUs that are being used to drive high performance computing today. The thing that's an expensive part, I'll say, of doing a computation is in communication. So we have to pass information from one process to another, and that passing of information is done through messages. It's done through MPI, and it turns out that that particular thing, communicating, is very expensive on the supercomputers when compared to the floating point operations. So floating point operations are relatively cheap, and message passing communication is relatively more expensive. So that's a change in some sense in how we used to think about computing. We used to think about computing in terms of the floating point being the most expensive part, and today that's changed quite a bit. And the other thing to realize is that we have different levels that we can use to do our computations. Much of scientific computing in the past has been done using 64 bits of precision. So we have a word, and that word has 64 bits in it, and we multiply and add operands which have 64 bits of precision, getting a result which is 64-bit accurate. And we can think about 32-bit, that's considered short precision or half precision. And then more recently, we have 16-bit and 8-bit floating point arithmetic. The 16 and 8-bit floating point arithmetic has been provided to help applications that use machine learning. Machine learning, it turns out, can get away with short precision. It doesn't need all of those bits of accuracy, and the hardware vendors have adjusted their computing power so that it does that short bit of arithmetic at much faster rates than it can using the 64-bit or 32-bit. So today we see many architectures with 64-bit, 32-bit, 16-bit, and even 8-bit floating point operations in them. The fastest computers today are considered computers that are running at an exaflop. An exaflop is, when we're talking about floating point operations, we're talking about an add or a multiplication of a 64-bit operand. So we will be using 64 bits when we describe the performance here. So one operation, one flop, is an add of two operands, both having 64 bits. or one flop is a multiplication where we take two numbers, 64-bit numbers, and multiply them together. So an exaflop is a billion floating point operations. So that's 10 to the 18 floating point operations can be completed every second on this on the fastest computers, and that fastest computer would be called an exaflop computer at that point. So that's where we are in terms of the state of the art. To think about an exaflop, to think about a 10 to the 18 operations. If each person on Earth were to do one calculation a second, it would take more than 4 years to do a billion operations, or 10 to the 18 operations. So 4 years for everybody to computing on Earth to do what this computer can do in 1 second, just to put that in contrast or relief. So it really is quite an astounding amount of computation. I became a benchmarker back in 1979. We were developing a project called Linpac. Linpac was a project developed by the National Science Foundation. It was funded by the National Science Foundation and the Department of Energy. And it involved 4 groups. It involved, in this picture here, the person on the right is Jim Bunch. He was from the University of California, San Diego. That's Pete Stewart from the University of Maryland, Cleve Moeller from the University of New Mexico, and that's the 1979 version of me with a little bit more hair. That's my car that we're leaning on. That's the license plate that I had when I was a student at the University of New Mexico, and we worked on the Linpac project during that time. We produced a user's guide for Linpac, and in the appendix to the user's guide, I put together a little table that listed the performance of about 20-some machines. It listed the performance, how fast they were able to solve a system of linear equations. That linear equation was of size 100. So think about a matrix problem, AX equals B, and think about solving that using a very standard algorithm, Gaussian elimination with partial pivoting. The Linpac user's guide has that routine in it, and I put together a benchmark that solved that system of equations. So this is a table this is the table that's in the appendix of that user's guide. It shows 23 machines. It lists the performance or the time it took to solve a system of equations of size 100. The fastest computer was a machine called the Cray 1 that was at the National Center for Atmospheric Research in Boulder, Colorado, and it ran at a rate of 14 megaflops, 14 million floating point operations per second. So that was back in 1977. A lot has changed since then. A number of years later, I had a list. That list of 23 machines grew to be a list of a few thousand machines. I had a colleague in Germany, Hans Moyer and Eric Strohmeyer, who had a list of the fastest computers, and they suggested we put together our list of their fast machines and my benchmark results, and we call it the top 500. So that's the current thing that we use to rank supercomputers, is called the top 500. It's based on solving a system of linear equations. That system of linear equations then gives you a ranking in terms of the fastest computers. We only list the 500, the fastest computers in this list. The list comes out twice a year. And again, we're solving AX equals B. The ground rules say you must use Gaussian elimination with partial pivoting. I'm going to give you a matrix. You have to solve that matrix problem. I'm going to give you a matrix A and a right-hand side B, and you have to find X using that algorithm. And you can implement the algorithm as fast or using the best techniques as you can. And then we're going to look at the rate of execution to compute this flops per second rate, and that's going to be used as an entry point. So the list comes out twice a year. It comes out in November and also in June. The most recent list is from November of 2022, and it shows the rankings then for these computers. So this is, in some sense, a snapshot of high performance computing going back to 1993 when we started. The red dots indicate the fastest computer. So today, the number one computer is at 1.1 exaflops. The computer that's on the bottom of the list today, that's at 1.73 petaflops, or 1.73 times 10 to the 12 floating point operations per second. So that's the bracketing, if you will, for high performance computing. And we can see a lot of trends and so on. So the blue line is the sum of the 500 computers. That's an artificial Excel sheet computation. But back in 1993, the fastest computer was a machine at Los Alamos National Lab. It was used for nuclear weapons design. It was a computer called the Thinking Machine CM5, and it had 1,000 processors. I'm giving a talk on a laptop, and my laptop has the ability to solve that benchmark problem. And when I solve that benchmark problem, I get 426 gigaflops. So that my laptop is really faster than that number one machine back in 1993. In fact, it's equivalent to a computer that was number one in 1997. It was a Hitachi machine with 2,000 processors at the University of Tsukuba that was used to do many numerical computations that were of importance to the people in Japan. So a lot has changed in a very short period of time, and that change is continuing today. So this is a list of the top 10 supercomputers in the world. So the number one computer is this computer at Oak Ridge National Lab, as I mentioned. It's called Frontier. It's integrated by HPE. That's a computer company. They don't make chips, they integrate things. So they take AMD parts, they take AMD processors and AMD GPUs, and they put them together with an interconnect called Slingshot from a company called Cray, and they make a supercomputer which they sell. And that supercomputer has 7.7 million cores or processors in it. It reached 1.1 exaflops, and that's 65% of the theoretical peak performance. So think of the theoretical peak as a paper and pencil computation by looking at the cycle time of the machines, of the processors, looking at how many operations you could do per cycle, and then computing the execution rate if you did nothing but those floating point operations. So when you run the benchmark, you get 65% of that peak performance, let's call it. And you could see how that varies with other computers on the list. The computer these supercomputers are very, they need a lot of power. So the Frontier machine needs 21 megawatts of power to run. So this benchmark, when running, you consume 21 megawatts of power. Think of it like this: a megawatt here in Tennessee, where I live, if I use 1 megawatt for 1 year, I would get a bill from the electric company for about $1 million. So that's a megawatt year, $1 million. And so this computer, this Frontier computer, consuming 21 megawatts, that's going to be running for many, many years. Every year, the power bill for the computer is roughly $20 million, 20 million US dollars. So you could see these are very expensive machines to run. The computer itself cost about $600 million, and it's very, very powerful. So when we look at the top 10 list here, we see the US has five computers. There are 2 computers in China. So China has some computers that they're designing on their own. They're not done by Western companies. This first one here, the Sunway Tahu Lite, is actually using a Chinese chip from Sunway. It's a chip which has 260 cores on it, and it's number 7 on the list. There's another machine that's number 10, the Tianhe 2A, and that machine is using Intel parts. While a number of years ago, China was still allowed to use Intel parts, today there's an embargo against China from using parts from the US companies. So they're changing this architecture today to replace these Intel parts with processors that are designed in China. They're going to be using ARM. They're going to be using an ARM processor to drive this computer in the future. So this gives you a sense of the computers here. The red indicates that they have accelerators or GPUs. The one that doesn't have a GPU is this machine from Japan called Fugaku. It's based on an ARM architecture, which uses vector instructions to help boost its performance. And you can see the performance rate. They actually do very good in terms of their theoretical peak. They're running at 82% of the theoretical peak of the machine. So 5 in the US, 2 in China, 1 in Japan, 1 in Finland, and 1 in Italy for the top 10 machines. These are very powerful systems being used to do advanced computing. The number 1 system, I'll just want to talk about it just briefly here. It has the peak performance of 2 exaflops. So 2 times 10 to the 18 floating point operations per second. Each node of this computer has 1 AMD CPU and 4 AMD GPUs in it. And it has 9,408 nodes in the machine. And the interesting fact is that if we take a look at the performance, if we use short precision, 16-bit floating point, instead of 2 exaflops, that's for 64-bit floating point, at 16-bit operations, the performance jumps to a peak of 11 exaflops. So, there's a factor of 5 there in terms of the boost given by using that short precision in it. We also noticed that most of the performance, 99% of the performance from this computer comes from using those GPUs. So you really need to be using that component, that GPU in these systems in order to be getting the fastest execution rate. This is looking at the number 1 computer over time based on the top 500 data. You could see how it's changed. We reached what was called the teraflop, 10 to the 12 operations back in 1997. 11 years later, we got 3 orders of magnitude in getting to a petaflop, and then it took us 14 years to get to an exaflop from that point. So 3 orders of magnitude going from tera to peta in the 11 years, and then going from peta to exa, it took us 14 years, and we would expect carrying on into the future, it's going to take even longer. So things are slowing down, and that slowdown is coming about by a number of things. Some of it driven by Moore's law, other things driven by something called Dennard scaling, and it's just harder to get the performance. So if we take a look at a projection here, the blue is giving us an indication of where the number 1 computer is today. It's just over 1 exaflop. And we see that we're going to reach an order of magnitude greater performance, 10 exaflops, based on this projection here in 8 years. So it's going to take us a long time to get 3 orders of magnitude to reach the next large threshold, which would be zetaflop computing. So we'll have to see how that evolves over time. If we take a look at the supercomputers and look at where they're located, China has the most supercomputers. So there's 162 of the 500 fastest computers. China has 162. US has 125. Germany, Japan, France, the UK, etc., have those numbers associated with it. China also produces the most supercomputers. So not only do they have the most supercomputers in their country, they make the most supercomputers, which they then sell worldwide. So they have 5 manufacturers in China: Lenovo, Sugan, Inspur, Huawei, and the National University for Defense Technology has been designing and building supercomputers for many years and has been deploying them. There are also rumored to be 2 exascale computers in China, but those computers have not run the benchmark, or they haven't submitted the benchmark so that they're listed in the top 500 list. So the first one is a machine called the Sunway Ocean Light. That's a follow-on to the previous machine that is listed in the top 500. And it's reputed to have over an exaflop for Linpac. There's been scientific papers written about this computer, so we understand the architecture very well. There's also another machine in Tianjin in China called the Tianhe 3, and that uses ARM processors and an accelerator. And also it is reported to have performance above an exaflop for the benchmark, but they haven't submitted the results. And I think there's concern in China if they were to submit results, it would probably cause more issues with computer parts going to China. So I think they're just lying low and not letting these machines be widely known that they exist. Supercomputers are used in industry. Industry provides, the ability to develop new and better products using high-performance computers. We see it being used in many areas. In fact, if you take a look at the top 500 list, about half of the machines, half of the computers are used in industry. So industry understands that these computers provide some strategic advantage for them in getting things, making better products. And they're being used in many fields. So as an example, they're being used in the oil industry for seismic data, trying to locate oil reservoirs or other things under the ground. They send a pulse on the ground. They look at the pulse and they try to reverse engineer what's under the ground based on the signals they get back from that. Aerospace industry uses high-performance computers to design better aircrafts, make them better structural, make them more efficient. The automobile industry uses supercomputers to help design lighter, more economical, more crash-worthy vehicles. In the old days, they would build something and crash it into a wall and see what happens. They probably do a few of those experiments, but most of the experiments are done using computer simulation on high-performance computers to be able to optimize the design of that product. And the chemical and pharmaceutical industry uses high-performance computers to design better drugs to combat certain diseases, or certain illnesses as well. Again, if we take a look at the market segment, now we're looking at the top 500 from the beginning in 1993 until today, and we're looking at a breakdown of where they're being used. We see that industry has 233 machines today are being used in industry. 119 of those machines are being used in research, and down the list you could see that. If we take a look at the machines in China, 134 of their machines are being used for industry purposes. In the US, 39 of the US machines are being used as an indicator for industry. So high performance computing is being used for simulation. It's being used to carry out simulation for climate, combustion, nuclear reactors, fusion, stockpiled stewardship, material design. It's being used in accelerators. And most of these problems are being simulated through the use of three-dimensional partial differential equations. So we use 3D partial differential equations to do the modeling, and those models result in a discretization, and that discretization leads to solving a system of equations. Very similar to the Linpac benchmark, we want to solve AX equals B, but here the matrix is not dense, it's sparse. It has a sparse structure associated with it, so there's not a dense structure. And that algorithm we used for the Linpac benchmark, Gaussian elimination with partial pivoting, doesn't work very well here. Because Gaussian elimination expects the matrix to have a lot of non-zeros, and these matrices that are used for partial differential equations are relatively sparse in nature. We use a different algorithm. We use an algorithm which is iterative in nature, and we use a method that we call the conjugate gradient method for solving it. So again, we're solving AX equals B. A is large and sparse. We have a right-hand side B, and we want to compute X. So we use an iterative process to do that, and we have a matrix which has this structure associated with it. It's sparse. It has that sort of non-sparse, non-zero structure associated with it. We have a discretization. In this case, it's a 27-point stencil operator that we use to discretize that 3D partial differential equation, and that leads to this matrix problem. So we have a benchmark now which uses this algorithm, the HPCG. So this is something that's more like the real method that are used on computers. to solve 3D partial differential equations. So here's a list of the top 10 machines for doing HPCG. I've listed here the Linpac number. HPL is the Linpac number for the machine. The number one system for solving HPCG is the machine in Japan, and it had a Linpac number of 442 petaflops, and it has a number. The rate that it solved this benchmark is 16 petaflops. So you see the difference there between solving a dense matrix problem as opposed to solving a problem which is based on a sparse structure associated with it. And I've listed here the percent of peak performance. So in the best case, we're getting 3% of the peak performance of this computer. And if we take a look at the exascale computer, the machine at Oak Ridge, in this case, we're getting just 0.8% of the peak performance of the machine. So less than 1% of the peak performance. So that's a warning in some sense that that high level of performance is something which is going to be very hard to obtain on this computer. So this is a graph here which gives us an indication of the top 500. The black dots are the theoretical peak performance. The green dots are the Linpac performance numbers. And if we look at the HPCG numbers, they're much less. And that shows us a bracketing, if you will, from the blue is really the real applications, and the green is where we are with the benchmark that was designed in the late 70s, where floating point arithmetic was very expensive. Today, floating point arithmetic is not expensive, and the communication is really the expensive part. So this new benchmark reflects better on the communication. So if we take a look at the top 500 machines and how they've changed over the years, what we see is that Intel has been supplying parts for supercomputers for a very long time. But more recently, Intel and AMD, both of which use something called the x86 instruction set. Both of them really dominate the top 500 list. So we see, 97, 98% of the top 500 machines are using Intel commodity processors, or AMD commodity processors, which are based on x86 architecture. Only 5 computers on the top 500 list are using ARM processors. ARM is probably the most common processor. It's used on our cell phones. And at some point, we would expect the ARM architecture to also become a more dominant player in this way. The other thing that we have is that we have accelerators coming from really just a few companies. NVIDIA really dominates the accelerator market. So those GPUs are coming from NVIDIA. The interconnect for our high performance computers are really based on Ethernet or InfiniBand. They dominate the internet, the interconnects on the supercomputers, and we see Linux everywhere. So we have commodity processors, commodity interconnect, commodity GPUs being used on our systems, and that, of course, is driven by cost. So we want to buy a low-cost machine which has high performance, and if we could buy something off the shelf rather than to design it ourselves, we would be in a better position for the cost. When we look at high-performance computing, we typically see a small amount of data that comes in, and then we have a numerically intensive computation that takes place, and a large amount of data that comes out. So that's what we would consider more a traditional high-performance computing application that's very numerically intensive. Here's an example of that. We're looking at the climate model as it evolves over time. We have a small amount of data that goes in, and we get this very rich view of what's happened over time as output from that. And that's sort of in contrast with the high-performance data analytic solutions that we have. They have a large amount of data going in, That data going in is used basically to train the models, and then we have a small amount of data coming out, the answer that we're looking for from machine learning. So a large amount of data going into machine learning and a small amount of data coming out. Quite different than what we see for scientific computing. Usually we're thinking about 64-bit input. The simulation is done in 64-bit, and then a solution comes out, which is represented as 64 bits of data. With machine learning, there's 16-bit floating point operations as input to the learning process and inference process, and then the solution comes out as, again, just a 16-bit output. So it's quite different in terms of the numerically intensive and the data intensive applications that we have. So machine learning and artificial intelligence have been around for a long time, but they've really taken off quite recently. And the question is, why did that happen now? Well, we have this flood of data, especially with the internet, to help train the models that we have. So we're pulling data from all over the internet to train specific components of these models. We have this increasing computational power that comes from these GPUs that we use. We have progress that's been made in terms of the algorithms and the theory behind the artificial intelligence and machine learning that have been developed over the last few years. And we have this increasing support from industry that's embracing machine learning and using it to help them drive what they're doing. And that also happens, of course, in scientific computing as well. We see machine learning being used in many areas. And we see a lot of hardware that's being designed specifically to help with machine learning and artificial intelligence. So these are some of the companies that have produced hardware that are really intended for use within the machine learning process. Companies like Cerebras and SambaNova and GraphCore all have tools that can be used to help boost the performance. You know, artificial intelligence is a large area, and we can think of breaking it out into smaller groups. There's one component that we think about machine learning that helps us. There's also natural language processing. If you've used ChatGPT, that would fit into this niche here. Expert systems are another form of artificial intelligence, vision recognition, speech processing, speech to text and text to speech, and robotics and planning all are part of the artificial intelligence revolution. So machine learning is important. It's a vital part of computational science. It's a tool that computational scientists are using, and we see it being used in many areas: climate modeling, biology, drug design, materials, high energy physics are all using machine learning today to help drive their understanding. So today we see supercomputers being built with commodity CPUs and GPUs. And the question might be, what happens in the future? Well, I predict that in the future we're going to have many more things added to that ensemble. We'll have CPUs, GPUs, machine learning devices. We'll have neuromorphic computing, maybe quantum computing as an add-on to this ensemble. Tensors and optical computing all have a place that could fit into this as we go forward into the computing, into looking at better ways of doing our computations. And we might be able to dial up, the number of these components that we have on our supercomputers to give us the right balance for the applications that we want to solve. So in conclusion, hardware is in constant state of change. We go from scalar to vector to distributed computing to accelerated, and we have now mixed precision. There are these three computer revolutions that have taken place. High performance computing is one, deep learning is another, and edge computing, which I really haven't had a chance to talk about, is yet a third level. Algorithms and software are critical for all of this, and the advances that we see in the algorithms and software really follow from the hardware. So the notion I have is that supercomputers are designed, the hardware is designed, and it's thrown over the fence, and it's left up to the applications people to look at the design of algorithms and the implementation of that in software to fit onto the hardware that they've been given. And sometimes it takes a long time to get an optimal match between the hardware and software. And we're not going to be doing that very efficiently initially, and we'll have to refine that over time. There was an interesting paper written by Charles Leiserson that appeared in Science in 2020, which described this. In fact, the title of their paper was "There's Plenty of Room at the Top. What will drive computer performance after Moore's Law?" It's a riff on Feynman's 1959 lecture about there's plenty of room at the bottom, where he was talking about quantum computing and looking at how things can be designed at that level. So that's sort of where we are today. There's plenty of opportunity here to develop software and algorithms for high performance computing that fits with hardware development. So thank you so much for your attention, and I guess we'll answer some questions in the follow-up. So bye for now.